Hi class, it's me, Professor Williams again. I'm here to make the next video in our series, Chapter 3.2, which is on radian measure and the unit circle. So, we will be applying arc length on a unit circle and the area of a sector of a circle. Sorry, not on the unit circle, but of a circle. Okay. So arc length. Arc length is the length along the curve of a circle. Okay. It's called an arc because it's not the full circumference. It's a portion of the circumference, right? It's a small piece of it. So the length S of the arc, okay, so here they're showing equivalent sort of things, okay, on a circle of radius R, right? So our circle here has a radius of R, made by a central angle of measure theta, right? Theta radians is given by the product of the radius and radian measure of the angle. So it's given by the radius, okay, times the angle. So if I have an angle here and I open it up partially, okay, then that is a portion of an entire circle. Okay, so that's a portion of an entire circle, right? So it's a portion of an entire circle. So the way that we find this, so remember, the circumference of an entire circle is 2 pi r. Okay, the 2 pi stands for 360 degrees, right? In radian measure, 2 pi is 360. So if I'm only going an angle of theta, okay, then it's going to be r times theta is going to give me the length that I traverse around the circle. If I were to go halfway around the circle, that's 1 pi, right? That's 1 pi radians. So that would be pi times whatever the radius is. And in fact, in order to go all the way around, that's 1 pi, 2 pi. Okay, so that's where this formula comes from. If you were not aware of that, right? So here S equals R theta, where theta is in radians. So a word of advice, right? When we use this formula, it has to be in radians, not degrees. You cannot go 360 times R. That's not going to work. It has to be in a radian measure, right? So in terms of pi or in actual radian values, because remember what pi is? Pi is a number, right? 3.1415962, yada, yada, yada. So that's a number. So pi times R is 3.14562 or whatever it is, times whatever that R value is, right? So we can always leave it in terms of pi. That's always actually the preferred value because that's our exact value, rather than having to round things because we're using only so many decimals of pi, right? So let's do an example, okay? So we're going to use our formula here to find an arc length. So a circle has a radius of 18.2 centimeters, okay? We want to find the length of the arc that is intercepted by a central angle with measure 3/8 pi, right? So what that means is we have 3 pi over 8 radians and a radius of 18.2. So what is the length of the arc that's created by that measurement, right? So again, 18.2 centimeters, right? And that rotates by 3 pi over 8 or 3/8 pi. What is the length at the end of the radius that the end of the radius sort of extends along the circle, right? What is this length here? So again, we know the formula here. We're already in pi, we're already in radian mode, so that's fine. We really just have to multiply 18.2 times our radian measure. Okay, so S equals R theta. So I'm just replacing R with 18.2 and I'm replacing theta with 3/8 pi, right? And now that I've done that, my end result is going to be in centimeters because the radius is in centimeters. And so that the end of the radii here, it's going to traverse some sort of amount of centimeters as well, right? So when I do this multiplication, either on my calculator or by hand, again, you can go 18.2 times 3 and then divided by 8 and just leave that over pi. or you can actually multiply your value of pi in and have a decimal form. I would suggest you cut it off at 2 decimal places after you multiply by pi, because we're given 2 decimal places. However, you should probably just keep 2 decimal places and just keep the pi at the end anyways. It's generally the preferred method, but here, however, especially since we have a unit of measurement, it's 21.44 centimeters. So here they're multiplying the pi into the answer, right? So here they have 18.2 times 3 times pi, divide that all by 8, and that should give you 21.44. Okay, so notice we're given 2 decimal places. Our answer is in 2 decimal places. Okay. Example B. Let's say our circle again has a radius of 18.2 centimeters, and we want to find the length of the arc intersected by a central angle with measure 144 degrees. So here the problem that we're having is that we are in degrees. So before I can do this, I need to transform my degrees into radians, right? I need to have the equivalent angle measure, but in radian mode. So I'm going to convert my degrees to radians. So again, to do that, we have our transformation constant, right? So this is pi over 180. Again, this is really just a 1 because pi and 180 are the same thing. So I'm really just multiplying this value by 1. It's just that I'm doing so in a way that it'll change it from degrees into radians, right? So this is my conversion factor. So this turns into 4 pi over 5, or 4/5 pi, however you want to describe it. So again, what I'm doing here is I'm not writing this in decimal form, right? I'm reducing my fraction down to simplest forms. So S is our theta. Theta is now in terms of radians, so I'm okay. I can just multiply this times 18.2. We'll multiply everything out, and we'll have our values in decimal form. So when we plug in our values, we get 18.2 times 4/5 pi, which gets us 45.74 centimeters. Again, notice that we're at 2 decimal places because we were given 2 decimal places in the problem. Right? So let's say we want to find the distance between 2 cities. Okay, so for us, we generally think of distance between 2 places on Earth as a flat straight line, right? But the Earth is a sphere, right? It's round. So in order to calculate the actual distance, we have to use an arc length, okay? And so that's when we talk about latitude and longitude, right? So latitude gives a measure of a central angle with the vertex of that angle at the Earth's center, and whose initial side goes through the equator and whose terminal side goes through your given location. Okay, so all latitude measures are from the center of the Earth to the equator, and then the other side goes to whatever position it is that you're looking at, right? So Reno, Nevada is approximately due north of LA, right? So the latitude of Reno is 40 degrees north, and Los Angeles is 34 degrees north, which should make sense because this is closer to the equator, so it has a smaller latitude than Reno, right? So the N in the latitude means north of the equator, okay? The radius of Earth is about 6,400 kilometers, okay? Find the north-south distance between the 2 cities. So the central angle that's between the 2 is the difference between the 2, right? So from 40 to 34, that gives you a difference of 6, right? So we have a 6-degree difference in latitude. So if this is the equator, if this is Reno, if this is LA, we have a 6-degree difference between them. The angle measured between the equator and Reno is 40. The angle measured between the equator and LA is 34. So again, just to reiterate, you guys, whenever you have an application problem, draw a picture. Okay, that's always the first thing that I ever do in any sort of math course, is I always tend to draw a picture. So most of the time pictures are provided for you, but not always, right? So you want to be able to get in the habit of drawing a good picture from the description given. So we're in degrees, which we don't want to be because this is an arc length. Okay, so we need to convert this into radians, and so we know the radius, okay, 6,400, right? So from here to here, the center of the Earth to LA, the center of the Earth to Reno is about 6,400. Okay, maybe a little bit different depending on your elevation, right? And the angle measured between the two is going to be 6 degrees. So that's all the information that I need in order to find this arc length, right? I have a radian measure, which I'll find right now, and I have a radius. So 6 as a radian is going to be 6 degrees times pi over 180. Remember, on the bottom is what you are transforming from. The top is what you are going to, right? So I want to go to pi, so I need to cancel out the degrees, right? So the degrees will be on bottom, so it cancels with the given degrees. So 6 over 180. So remember, 6 times 3 is 18, so this should be 1 over 30 times pi, right? Or pi over 30, however you decide to call it. So the distance between the two cities is given by this length S, this arc length. So we're really going to take pi over 30, and we're going to multiply it by 6,400. So notice that we'll have some zeros that cancel off, and then I'll basically have 640 divided by 3. 3 also goes into 64 evenly, semi-evenly, I guess. So this is the equation that we're going to set up. We can just plug this straight into our calculator if we're not strong with our algebra, and we should get about 670 kilometers, especially if we multiply this pi in, right, to get the actual measure and not in terms of pi kilometers, right? So the north-south distance, okay, between Reno and LA is about 670 kilometers. So let's go to our third example now. We're finding a length using S equals R theta again. So here we have a rope that's being wound around a drum. Okay, the drum has a radius of 0.8725 feet. How much rope will be wound around the drum if the drum is then rotated around its center by 39.72 degrees? Okay, so I put the rope on, and then I rotate the drum a little bit, okay, and I want to know how much rope has been wound around this drum, just this small portion here, okay. And again here, I know when we think of drum, we generally think of an instrument, okay, so this could be an instrument. This could also be a metal drum, such as a pulley or something to that effect, right? So it's pretty straightforward. I'm in degrees. I need to be in radian measure, right? I know my radius, so all I really need to do is the same thing I've been doing so far. Let's convert this into radians and then multiply it times my feet. So maybe you want to go ahead and pause it and do that yourself and just check and see if you get the same answer that we're about to get ourselves, right? So go ahead and pause it in 3, 2, 1. Okay, so hopefully you took the time to go ahead and try this out yourself, and you're going to be just checking your work. I know that the write-ups that we have, the work is pretty much identical, just different numbers for the most part. But it's always good to kind of go along with the videos, right? So the length of rope wound around the drum is the arc length of a circle, right? Because it's wound around this drum. The radius is 0.8725, and the angle is 39.72 degrees. So if we use our formula, okay, we first, of course, need to convert this into radians. Okay, so we can just plug it all in all at once if we want to, right? Instead of doing it in pieces. So I have my radius, I have my angle in degrees that is being converted into radians all at the same time. So now it's just one problem that I can just plug into my calculator, right? So I can plug in this times pi, and then divide whatever answer I get there by 180, right? Or I can throw it all into the calculator all at one time if I use the appropriate parentheses in the order that's shown. Okay. So at the end, you should get less than a foot. So 0.6049 feet. So again, notice that your decimal places match up with the largest amount of decimal places that was given to you in the problem. Okay. Example 4. So here we have 2 gears that are adjusting so that the smaller gear drives the larger one. And that's generally how gears work, right? You have one gear turns another gear, which possibly turns another gear, and so forth and so forth. If you've ever seen a clock, right, or a watch, you take a watch apart, you have several gears. There's one central gear that turns another gear that turns another, and so forth and so forth. So right now what we're doing is we're just putting 2 gears together. Okay. The smaller gear is going to rotate through an angle of 225 degrees. Okay. So this is the picture that we have. The small gear has a radius of 2.5 centimeters. The large gear has a radius of 4.8 centimeters, almost twice as large as the small one. The small gear is going to rotate 225 degrees, right? So more than 180. And so what we want to know is, so you can think about it as this, right? If we start right here and we rotate 225 degrees, how much is this then going to rotate? And it really depends on how much contact the 2 gears have with each other, right? So if this rotates 225 degrees, right, then the arc length of 225 degrees is how much contact we will have with this gear. And the amount of contact that we have between this gear and this gear is how much this gear is going to turn, right? So what we're going to do is we're going to find the angle, sorry, not the angle measure, the arc length of this, okay? And the arc length of the small gear will be the same as the arc length of the larger gear, okay? And so we will have the arc length and we will have the radius, but we won't know the angle, but we have a formula where we know 2 of the elements, so we can solve for the one thing we don't know, which is the radian measure here. Okay, so first I got to kind of apply my my arc length formula to the small gear, and then use that information to figure out what's happening to the larger gear, and then use that information to find my angle measure. Okay, so I think we kind of repeat that process, that statement right here, real fast, right? So first find the radian measure of the angle of rotation for the smaller gear. Then find the arc length on the smaller gear, and this arc length will correspond to the arc length of the motion of the larger gear as well, right? So basically, a more compact way of saying what I just told you here, right? So if we convert it to 25 to radians, very straightforward. Again, we just multiply by pi over 180, do our canceling, and we should get 5/4 pi radians. Okay. So now I know what the angle measure is for the small gear, and I have the radius, right? So I take the radian measure and the radius to find the arc length. Okay. So I just plug in 2.5, the radius, and the radian measure, and I get 12.5 pi over 4. Now, you might be saying, Professor Williams, all these other problems, we went straight to the answer. Well, we're going to continue to do math with this value. So if I were to write a 1 decimal place approximation, I'm going to get a rounding error, right? Because I'm multiplying by a value that goes on forever and ever and ever. It's always best to not round into the very, very last step. So I'm going to keep the value I have now as is, and I'm going to continue to do math with it until the very, very end, when I can give my answer by multiplying in pi and all that stuff at the very, very end. Okay. So I have my arc length. So now I know the arc length for the larger gear as well, and I have the radius. So I'm going to use this arc length, S, and my radius, R, to find the radian measure for the small gear. Now, just to check real quick, okay, our question here wants to know how many degrees will the larger gear rotate. So when I'm done here and I find my actual radian measure, I got to make sure I transform that or convert that back into degrees at the end, because it's asking me for the degree measure that this larger cog, this larger gear rotates. So make sure you're answering your question completely, right? So here, if I simplify this, because there's no such thing as decimals inside of a fraction, you have either decimals or you have fractions. You do not have a mixture of both. So that's what they went ahead and did here, right? You can think about this as 12 over 4. Really, the easiest way to convert this into a single fraction is to convert 12.5 into a fraction. So that would be 25 over 2 over 4, and then simplify that improper or that complex fraction into 25 over 8, okay? So an arc with this length on the larger gear corresponds to an angle measure theta, right? So again, I'm going to use this formula. I know the arc length, I know the radius, I don't know the radian measure, so I'm plugging in my 25 pi over 8, I'm plugging in my radius, I'm going to divide both sides by 4.8, okay, and I get 125 over 192. Again, what I could have done here, something easier to do to keep it in fractions, because honestly fractions are easier to deal with, is I would convert this into a fraction value, right? So this is really 4 plus 8 tenths, right? This is in the tenths place, so I could say 4 plus 8 over 10. Convert that into an improper fraction, which would be 48 over 10, right? Or just understand that this is in the tenths place, right? So 48 over 10. And so I would multiply this then by 10 over 48 in order to divide it. Okay, so again, just some standard algebra, playing with some fractions here, in order to get an exact value. Okay, so my exact value for theta is 125 pi over 192. Again, if you're playing with decimals this whole time, you would then have some crazy long decimal here that you would still need to convert into a degree measure. So the nice thing about this is that my pi is here. So when I convert this into degrees, I just have to multiply it by 180 over pi so that the pi's cancel, and I can just do algebra on the numbers rather than trying to figure out what's going on with these decimals and do I need to divide pi out because it's in a decimal form. And it gets very, very funky basically. So let's take this and convert it into degrees. The pi's will cancel. These are both multiples of 2, so they can at least divide by 2. But really, I can just do the math here and multiply 125 times 180, divide that result by 192, and get my approximation of 117 degrees. Okay, so hopefully I didn't talk too fast for you guys and that makes sense to you. Mostly about this fractional stuff, right? So maybe go ahead and rewind that video and just slow it down a little bit and work through this yourself. Try to go from 12.5 over 4 to the 25 over 8. And then from there, when you set this up, see how you get it to go into 125 over 192. This is a very important skill to develop. You don't want to just, especially if you're going into the STEM field, which is why you're in trig, you don't want to breeze over some of these lower level skills, right? You want to develop these. You really want to be able to get comfortable with fractions and decimals. So definitely make sure you're okay with those. Okay, so again, just to reiterate, our larger gear rotates through an angle of 117 degrees. So area of a sector of a circle. So arc length and area of a circle of a sector are closely related. So again, we're going to be developing that today, right? So a sector of a circle is a small portion of the area of a circle. Okay, so if you, let's come back, right? So notice when, I'm sure we'll have another picture, But notice that when I'm talking about a radius traversing an angle and creating an arc, it also creates a slice of pie. Okay, and this slice of pie here is a portion of the entire pie. Okay, and so I know I'm saying pie, but I mean circle, obviously, right? I'm just hungry right now. So this small piece of the circle is a smaller area. It's a proportion of the whole area. Okay, so remember, the area of a circle is pi r squared. Okay, pi r squared. So remember what we'd say for circumference, right? It was 2 pi r. Right? Pi r squared is not 2 pi, it's only half of that. So the area of a sector is actually just half of your angle times r squared. Okay, so that's how you find this a sector, the area of a sector. So let's jump past this all the way to where we were. All right, so again, let's think about it as a piece of pie, right? So we have r, it traverses an angle, okay? It creates an arc length, and it also covers, it spreads over a small portion of the whole area of the circle. So it covers a small area of the circle ourselves. We call this a sector, okay? We like to know the area that this radius sweeps over in terms of the whole area of our circle, right? So the area A of a sector of a circle of radius r and central angle theta is given by the following formula, okay? Half of your angle times r squared. Now this should make sense again, because if you talk about the entire circle, right, which is 2 pi, okay, the area of an entire circle is pi r squared. It's half of the whole 2 pi, which is just pi, r squared. So you're really just applying that same formula, but to a portion of your circle. So it's a half of whatever angle you have times r squared. So again, the easiest way to remember these formulas, they're not hard to remember anyways, but is how are they formed, right? So if you just think about how this is in relation to the area of an entire circle, you should always be able to remember the area of a sector, right? Your arc length is related to the entire circumference of a circle. So your arc length formula should be fairly easy to remember if you remember what the circumference of a circle is, and then you're just kind of like pulling that back to a portion instead of the whole thing. That's the way it works for me, at least. And so I feel like that's most likely the easiest way to remember some of these formulas. Word of advice, okay? Just like for arc length, we have to be in radians, okay? You cannot be finding areas of a sector if you are in degree mode. You have to be using radian measures, okay? So let's say that we have an irrigation system. So basically they're talking about a sprinkler, okay? You have a sprinkler system that rotates over a 15-degree area, and the length of that sprinkler system is 321 meters, okay? So they're saying irrigation, so there's probably some piping and things like that, but this is the area that it covers, right? I feel, according to the picture, it might make more sense if you think about it as a big-ass sprinkler that covers a 15-degree spread, right? So if we want to find the area of the coverage of this irrigation, okay, basically what's being watered, we have a portion of a circle, right? So obviously it doesn't have a full circle for us, okay? But we can think of this as a portion of a larger circle, right? So we have what we would use as a radius, and we have an angle measure, right? So we would cut this angle measure in half after turning it into radians, and then we would square this radius. Okay, so we're going to convert 15 degrees to radians. So multiply that times pi over 180. Things will cancel fairly nicely, and we get pi over 12 radians. Okay, so now we need to use our formula that we have, which is 1/2 theta r squared. Okay, so 1/2. I prefer to put theta first because I think about it as cutting theta in half, not 1/2 times this thing. That's just for me, period, right? As I explained to you guys. But regardless, we plug our values into our formula and we can just throw it into our calculator. Again, this is an application. Applications mean that we need to have decimal value approximations, right? If I was just asking you, here's a regular old circle, give me these values, and there was no measurements, I need things exact. This is an application problem where we're talking about watering something. You can give me your approximate values here, okay? And that's it. I hope this was helpful to you guys. I'll see you guys on my next video, which is not coming back around until I think 3.4 maybe the next video I have to make for you guys. Okay, see you guys then.